Hello everyone, welcome to Agile Rankmate, your partner in education. Today we'll be starting a new series named Mindmap. Mind maps are flowcharts which are good for last minute preparations for your exams. And in this series we'll be covering mind maps for various chapters across various subjects. And for this video we'll be looking at grade 9 chemistry. The chapter name is Matter in Our Surroundings. In this chapter, or in this mind map, we'll be covering the basics of matter, the characteristics of matter, the types of matter, and the processes related to matter. So this is our main mind map of the chapter Matter in Our Surroundings. So as you can see, this mind map is a bit complex and it's not that easy to comprehend at first glance. So that's why we have divided this mind map into 7 parts. The first part will cover the basics of matter and the characteristics of matter. The second part, the third part, the fourth part, and the fifth part would cover the different types of matter that are solid, liquid, gases, and other less commonly known types of matter. And for the sixth part, we'll be covering the interconversion of states, that is, conversion between matters as a solid, liquid, liquid to gas, and gas to solid. And then at last, we'll be covering evaporation. So, let's dive into the first part, the characteristics of matter. So first, we'll be covering the physical nature of matter. Before that, let's define matter. Matter is any substance that has mass and occupies space or has volume. So, we have understood what is matter. It has mass, it has volume, basically anything that we can feel, that we can touch, or that is matter. So, the question arises, is matter continuous or particulate? That is matter made up of particles like these, or is it just one continuous block? So to find the answer for this, we have to look at an activity. So this is the activity we have. So if we look at this, first we had to take a beaker of water, and that's about 50 ml of water. And as you can see over here, there's a bit a million times magnified. We can see that there are spaces between this is the water particles, and we'll further prove that matter is made up of particles. So if we add a bit of salt into this beaker, and after adding the salt, we can see that the salt settles down over here. But if we stir the water to fasten the process, then we can see, if we check the water level in the first, it will be 50 ml. In the second, the last result, it will also be 50 ml. So you'll be asking, where did the salt go? Did it just disappear? No, it had filled in the spaces that were between the particles of water. So this, we had just explained that there are particles, that the salt is a particle, the salt is made up of many particles, the water is also a particle made up of many particles. So with this we can prove that matter is particulate and is made up of particles. So next, we'll be looking, how small are these particles? So we had seen in the previous slide that matter is made up of particles and are particulate. So after that, we had to ask ourselves the question, how small are these particles of matter? Is it big enough to see with our naked eye, or is it very small that we need a microscope, a complex microscope to see it? So for this also we have an activity. So first we take 100 ml of water. Then we add a bit of a chemical known as potassium permanganate or crystals. We'll be adding crystals of potassium permanganate. And if you can see, the solution has turned purple when we mix it, and the potassium permanganate spreads all over the water particles. Then we can see that the solution is purple. It is clearly visible. Now we take another beaker of 90 ml water, and then we add 10 ml from the previous beaker into the next one. Now you can see that the color becomes light. If we continue to the next beaker, which also has 90 ml of water, and we add 10 ml from the previous solution, we can see that the color has gone even lighter. And if we continue doing this activity, we can see that the beaker would continue to have lighter and lighter colors. However, even if we do it many times, there will be still a little bit of color. So if we have to zoom in on this, when we transfer, if these are the water particles, when we transfer 10 ml from the previous solution, then some of the particles of the potassium permanganate crystals, these would be taken and transferred to the next solution, which also will have some of the particles. However, in this magnified image that I have just drawn, there are only some particles of potassium permanganate in this spot, but in reality there are many millions of particles of potassium permanganate in that one space. So if we take a bit part of the for example the first beaker, if we take a little, then there will be still millions of them in the second one. And if we take it to the third one, there are still even though less than the previous one, there will still be many potassium permanganate crystals. That's why the color would still there'll be still a little bit of color, even if it becomes lighter and lighter, but it doesn't disappear completely even if we do it for a long time. So with this we can prove that the particles of matter are very tiny and are present in large quantities. If we take for example a bottle of water or a little bit of water, it would have a large quantity of particles. So next we'll be looking at the characteristics of the particles of matter. So we have the first part characteristic, which says the particles of matter have space between them, particles of matter are continuously moving, and the third characteristic, which is particles of matter attract each other. So we'll be looking at each of these characteristics and activities which prove each of them. So for the first one, first characteristic is that the particles of matter have space between them. Now for this, the previous activities, the first activity which we had done to see if matter is particulate or continuous, and the second activity to see how small are the particles, both of them, with both of these activities we can prove that particles of matter have space between them. For example, the first activity, we saw that the particles of salt filled the spaces of particles of matter, and in the second one we can see that the potassium permanganate crystals filled in the spaces of particles of water. So this characteristic is already proved. Now for the next characteristic, which says that particles of matter are continuously moving. Now for this, let's take a candle or a fragrance, and if we keep our nose near to the fragrance, we can see that the particles of the gases would still travel from the candle onto the nose, which we are standing here. But if we keep our nose a bit far apart, even still we'll have a faint smell of the candle or the fragrance. Here we can see that the particles of gas, it reaches our nose even if we are near or far away from the fragrance. Thus, we can say that the particles of matter are continuously moving and still keeps on moving, has kinetic energy between them. So this characteristic is proved. Now, the next characteristic, which is that the particles of matter attract each other. So if we take a bucket of water and we put our hand in it, then we can see that the particles of matter, water, we can't actually see it, but we can feel the water has been separated away from us. So what is actually happening is that before we put our hand, the particles of water had been trying to attract each other. However, when we put our hand, they are still trying to attract each other, and that is how we feel the water between our fingers and which are trying to attract each other. That's the basic reason that we can feel the water. So with this activity, we have also proved characteristic number 3, particles of matter attract each other. Now we'll be moving to the next part of our mind map, which is states of matter. So the second, the third, and the fourth, and the fifth, which will be solids, liquids, gases, and the less commonly known states of matter such as plasma and Bose-Einstein condensate. So number 2, solids. Now if we look at the characteristics of solids, the molecules are closely packed in a solid, or we can say that the intermolecular force of attraction is more, or the intermolecular space is less, which basically the distance between the particles is less, or the attraction is more, as you can see in this image, which is a magnified one. We can see that there's very little space between the particles of solid. Another characteristic is that solids have a definite shape and a volume. So if we put a solid in a water bottle or in a beaker or in any other place in the earth, it will still have the same shape and would not change its shape depending on the container or the space it's in. However, it also has a definite volume and doesn't change it unless we cut it or do anything to it. So another characteristic is that it is hard to compress. So let's say we take an iron rod, and if we try to press it, then it'll be very hard, and we would need something like a compressor to press things like it, or to compress solids. It takes a lot of machinery, and we can't do it with our own hands, so it is very hard to compress. So if we look at examples which we have studied, is ice, wood, bottles, plates, chairs, tables, or many other things, iron, etc. So all of these are solids, and we are looking at the conversion between solids and liquids, which is basically for water. Liquids to solid is basically freezing, and solid to liquid is melting, and solids to gases is sublimation, and gases to solids is deposition. Now look at the part number 3, which is the second state of matter, which is liquid. Now For liquids, we can say that the molecules can move within the container, or we can say the intermolecular force of attraction is more than that of solids and less than that of gases. Basically, in the middle, it would have little space between the molecules, and thus the molecules can move within the container. For example, if we put a liquid in a water bottle, it would take the shape of the container. And if we take water in, let's say, a beaker or a flat container, we can say that the liquid takes shape of the container. For example, over here in the glass of water, the liquid is about this level and it has filled in the spaces, while if it were in a pot, it would still fill in the shape of the pot. And liquids, they do not have a definite shape, but they have definite volume. Now, examples of liquid is milk, water, oil, etc. And we have discussed solid to liquids and liquid to solids. And if we have to see gases to liquids, a liquid to gas is evaporation, but this is only a type, and the more scientific vocabulary is vaporization, which is different from evaporation, but we'll be discussing that in the later stages. While gases to liquids is condensation. So next, the fourth part of the mind map, which are gases. So gases, the molecules spread out, or the intermolecular space of attraction, the intermolecular force of attraction is less, so they can easily spread out. Similar to liquids, occupy the shape of the container. However, they have more kinetic energy, means they can move very fast from one place. So if we are to open a bottle full of gas, then it would quickly spread out before we can close it, and many amount of gas would have been lost into the atmosphere. And they also, like liquids, occupy the shape of the container, as we have discussed. And these gases can be compressed very easily. For example, if we wave our arms to the air, then we are basically compressing or moving the gases. And if we put both of our hands together, then maybe we are trying to compress a type of gas in the atmosphere. And example of gases are air, hydrogen, oxygen, nitrogen in its basic form, and then etc. And we have already discussed the conversion between liquids and gases. However, we'll also be discussing the conversion between all of the states of matter in later slides. Next, to the fifth part, or the fourth types of the state of matter, which are the less commonly known states, which are plasma and Bose-Einstein condensate. So plasma is basically when we heat gas even more, then the gas would start carrying electrical charge. So basically, a plasma is a mixture of electrons and nuclei. And these particles of plasma, they would give off light. Like for example, lightning is made up of plasma, is this overheated gas, atmosphere gas. And plasma TVs are also made up of plasma. And another example is the light in the stars, such as the sun. The light that they give out is basically because of plasma. And then let's look at another another state of matter which is less commonly known, which is Bose-Einstein condensate, which is discovered by Albert Einstein and J.C. Bose. And these, S.N. Bose, not J.C. Bose, discovered by S.N. Bose and Albert Einstein. And these, the particles of these state of matter, they are formed just above absolute zero, which means they can not be found anywhere in the earth. However, they can only be found in the depths of space. If we look closely into space, into the universe, then only we can find the Bose-Einstein condensates. They only exist just above absolute zero Kelvin. And however, both of these states are not necessary to be learned in this class. Both of them will be discussed in later classes. Next, we'll be looking at interconversion between the states. We have looked a little bit of it in the previous slides. However, we'll be looking at it more deeply. Now, in the previous slides, we saw that the conversion between solid to liquid is melting. However, the more scientific term we give it is fusion, which is basically if the particles of the solid, they are loosened, then they turn into liquid, then it's called fusion. And the opposite of liquid to solid, it's not freezing, but more scientifically we say it as solidification, which is basically the distance between the particles of matter are becoming more close and close. Now, from liquid to gases, the conversion of liquid to gases is known as vaporization. You may have studied it as evaporation. However, as we discussed, vaporization is not equal to evaporation. And we have a separate slide just for evaporation, and we'll be discussing in that. So next, if you look at from gas to liquid, it's condensation. The term, so the gas has many distance between the particles, and the distance between them will be shortened, and then they turn into liquid. And if we are to convert from solid directly to gas, then it's known as sublimation, and from gas directly to solid is known as deposition. An example of sublimation would be mothballs. So if they are kept in the open, then they directly convert to gas without being turned into liquids. So this is an example of sublimation. So if we are to delve deeper into the interconversion, we have to look at some of the factors in which the states of matter can be changed. The first factor is temperature. So we'll be looking at the effect of the change of temperature, and then we'll be looking at the effect of the change of pressure. So states of matter can be changed either by temperature or by pressure. So we'll be looking at both of these in the upcoming slides. So the effect of change of temperature. So for this, we take say a Bunsen burner, and then we keep a container, and we put a bit ice cubes at about maybe -30, -20, about that much degrees Celsius. And when we start heating the beaker, then it reaches zero, then we can see that the ice converts into liquid. And however, even if when we try to heat it a bit more, the temperature would still stay at 0 degrees Celsius for some time. But then after some time, it would start increasing. And when it reaches 100 degrees, the liquid water would change into water vapors. However, just like before, the temperature, if we try to increase it, it would stay the same in the thermometer for a bit amount of time at 100 degrees Celsius. and then however after some time it would start increasing. So we'll be looking, so we saw that when the solid convert to liquid and the liquid convert to gas, the heat did not increase for a certain amount of time. So what is happening? So this is the phenomenon we just discussed before, the water being heated, the ice being heated, and then when it reaches 0 degrees it melts, and then it's heated even a bit more, and when it reaches 100 degrees Celsius it evaporates or vaporizes, and then it takes a bit of time to a bit of heat is, even if it's given, it's the temperature is not increasing, and then the water is being heated. So why did the heat not show in the temperature or in the thermometer? So basically this amount of heat is known as latent heat. Both of these is known as latent heat. So this heat is used by the molecules. It is used by the molecules to free away from each other or to decrease the intermolecular force of attraction. So basically in a solid, the particles have the force of attraction is very high, and when it changes to liquid, it needs a certain amount of heat to decrease the force of attraction, to break the force. There's a heat needed, and which is known as latent heat, which is literally means hidden heat. Latent in Latin means hidden. And if you look at the definition, latent heat of fusion is basically, fusion is, the conversion of solid to liquid. So latent heat of fusion is the amount of heat required to change 1 kilo of solid to liquid at liquid state at atmospheric pressure at its melting point. That's the latent heat of fusion, while the latent heat of vaporization is basically the same thing, but just from liquid to gases. So let's continue and look at the next factor, which is pressure. So we'll be looking at the effect of change of pressure. So for the first example, we have gas, CO2 gas. When pressure is applied to CO2 gas, it converts into solid CO2, solid carbon dioxide, which commonly is known as dry ice. And this is an example of when we apply pressure to the carbon dioxide gas, it turns into solid. And another example is natural gas, which is commonly found as gas, as the name suggests, with petroleum. When we dig up petroleum from the sea, we find natural gas with it. And this is when we apply pressure to natural gas, it converts into liquid form, compressed natural gas, and it is stored in cylinders such as these. And there's another example of the effect of change of pressure from gas to liquid, and the previous one was gas to solid. So what happens when we put pressure? So in this activity, we see that when pressure is applied, the space between the particles decrease. For example, the first one, there are some spaces between the particles. Over here we can see it. While when we put pressure, we can see that the distance decreases and decreases, and thus changing the state of matter. So for the first one, if we have, if say this is a gas, then we apply pressure, then the spaces between them would decrease, and then we may convert it into a liquid, and then we again apply pressure and we can convert it to solid, or it may be direct from gas to solid, or any other type of conversion of the change of pressure. So basically the important thing is that the pressure changes the space. So if the gas has more space, liquid has less space, and solid has the least amount of space. So the pressure basically changes the amount of space between each of these states of matter. So if you have to summarize both of these factors, we have ice, water, and water vapor. So ice is basically solid, liquid, and gas. And ice is formed in less than 0 degrees Celsius, and liquids are formed at between 0 to 100 degrees Celsius. And water vapors or gases are we are looking at specifically the temperature of water and the melting point and the boiling point of water, and we have 100 degrees Celsius. So solids, the intermolecular space is less. In liquids, the intermolecular space is medium, while in gas the intermolecular space is more. And solids have less kinetic energy, gases have more kinetic energy, and liquids have a medium amount. So we saw before that the temperature, change in temperature means a change in the state of matter. So what basically happens in temperature is that the kinetic energy, example, if we apply heat to a solid, the kinetic energy between the particles, it is being increased and increased. As the temperature increases, the kinetic energy increases, and that's how they're converted into liquid. And again, if we heat liquid, the kinetic energy increases and increases to form water vapors. So the temperature is related to the kinetic energy. While next we discussed about pressure. While pressure, it is basically focusing on the intermolecular space. So if we have a solid would has less space between the particles, gas has more space. If we put pressure, it turns into liquid, and if we put more pressure, the spaces decrease and it turns into solid. So pressure is related to, say, the intermolecular space. So this is basically the interconversion between states based on pressure and temperature. So next we'll be looking at evaporation. So if we put our clothes in the sun, then we can see that the water in the clothes, they evaporate. So, but we can also see that the cloth becomes dry even if it doesn't reach 100 degrees. So as we discussed before, evaporation is basically a surface phenomenon, or we have seen the difference between evaporation and vaporization. Evaporation is a surface phenomenon. So if we have particles, if we put this in the open sun, then the temperature of this particle will be different from the temperature of this particle and this particle. This top layer of particle will have more temperature and the bottom layer would have less temperature. So the top layer of water, this would evaporate as the temperature increases, and then when it evaporates, the second layer would get the heat, and then it will also evaporate. And this is why it is called a surface phenomenon, because each of the surface evaporates and evaporates. So then vaporization, on the other hand, is a bulk phenomenon. What we say, a bulk phenomenon, which means that if we have the same glass, then all of these particles would have a change in temperature. For example, if a glass of water, it is directly, all of the particles are directly converted to gas. That is known as vaporization. But if each of the layer is converted to gas, that is known as evaporation. And this is the main difference between evaporation and vaporization. So that's all. We hope you found it interesting. So for more such videos, please subscribe to our channel Agile Rankmate. We'll be uploading more videos on the same. And until the next episode, take care, stay safe, ta-ta for now.